Hello everyone, in this video we are going to study about the asymptotic notations. So before we learn about the asymptotic notations, we need to learn about basic concept which you all might have studied ever in your life, that is order. So what is an order? And how you define it in an order? Okay, so I'll give you a small example, and from that you can actually understand what is an order. So let's say you are on Earth. Okay, so let's say this is Earth, and let's say this is Moon. So you all know that there is some distance between uh, Earth and the Moon. I think so. I'm not sure, but it's around this around approximately. Let's say it's 4 lakh kilometers. I'm saying it approximately. Actually, it's around, I think so, 384,000 kilometers. I think this is kind of the number. I'm not sure, but okay. I'm just for the sake of just for the sake of explanation, I'm taking this example. So let's say, now how can you write this number? How can you write this number? So this number can be written as 4 into 10 to the power 5 kilometers. So in okay, so this is the exact number which is used in scientific calculations. Okay, used in calculation. Okay, used in calculations. But if you see in general sense, in sense of a common man or common woman, you are going to say that the distance between the Earth and the Moon is in lakh kilometers. You are going to say like that. You'll not always know that, okay, always don't know about what is this here, but you will say, okay, it is in lakhs. What is lakh? What is lakh? That is 10 to the power 5, isn't it? Lakh is 10 to the power 5. So if you know that lakh is 10 to the power, that is equals to 10 to the power 5, then in general, you are going to say that the distance between us and the moon is in lakhs. You will not care about this 4 here. And you don't have to. So, in scientific sense, this 10 to the power 5 is the order of distance between Earth and Moon. This is the order. So, order is generally in these calculations is generally taken as 10 to the power some n, where n can be anything. N can be anything. Okay, it can be a fraction point, whatever it is. So what I have said like belongs to real numbers. Okay. So this is the order. Okay, in scientific. So what does it has how it has connection with computer science? It says computer science. How it has connection with computer science. So in the last video, we have seen that the asymptotic analysis which we do, the asymptotic analysis which we do asymptotic analysis is done for larger value of n, where n is input. Okay, n is input, where n is input. Okay, so asymptotic analysis is done for the larger value of n. Okay, so if the input is very large, okay, that is 10 to the power 4, 10 to the power 5. Okay, sorry, writing is a bit bad, no problem. Okay, so let's say the input is 10 to the power 4, 10 to the power 5 order, or maybe 10 to the power 6 order, 10 to the power 7, 10 to the power 12, 10 to the power 15. In real sense, these are very big numbers. These are very big numbers. Okay. So if the order is if the n is so large, then we actually, in general sense, like when you are calculating few of the things, like few of the making scientific calculations, then you will be needing the exact number. But in general sense, you don't need to analyze an algorithm. You don't need to have that exact constant. Okay. You just need to approximate. You just need to approximate the output graph. Okay. So let me take an example. Okay. Let me take an example. So what should I take? Okay. So there is something which is coming to my mind. Okay. There is something which is coming to my mind. Mm, let's say you are um uh, let's say you are taking I'm thinking, how can I make you understand this thing here? How to make this thing simple? Hmm. Okay, there is something which is coming to mind right now. Okay, so let me take like this. Okay. So we have seen about that the distance between the Earth and the Moon is 10 to the power 5 kilometers, approximately. Approximately. So what is this? This is a constant. This is the order, and there is the multiplication. So what is this? This is you can write it as CO kilometers. And this is a sense of scientific. So 40 power kilometers can be written in a common sense. Common sense. Okay. If we go in the same thing in the algorithm, the order order is generally given by the value of n, or you can say the nature of graph. Uh, so let's say it's an example. Let's say it's an example. Example. If let's say you have hmm, very bad. I'm going to take this here. I'm going to rotate the degrees here. Okay. Okay. So I don't think this is going to work. No problem. No problem. So let's say I'm going to have a Let's say I'm going to have a graph here like this, and then there is another graph like this. So these are, let's say, it's your input sides, input, and this is, let's say, you have, let's say, time increasing. So let's say there are two graphs. One graph goes like this, and then graph goes like this. Okay. So let's say this graph corresponds, let's say input is represented by small n. So this graph, let's say, and this is represented by t. So let's say this graph is represented by t to the power, and this is represented by 2t. This but normally used n. Okay. Now you know that okay, inputs will not be negative, so nothing will appear here or here. Nothing will appear here. Okay. So you are going to consider the right of the of the time axis. You are going to consider that. Now, next, can you see a similarity? Can you see a similarity here? Yeah, there is a similarity that both graphs are linear. Both are linear. Both are linear. So, so if the n goes to larger values, let's say 10 to the power 6, then 2 to the power n is 2 into 10 to the power 6, and n is equal to 10 to the power 6. And if you closely see, in common sense, this number doesn't even matter. Both of them correspond to the same nature of graph. That is, it is linear and it's going to give a very large number at a larger value of n. So that's why if you say the order, let's represent order as a very big O and a parenthesis. Let's represent the order like this. Then in that sense, order of 2 kilowatt is also n, and order of n is obviously n. So ultimately, the order of n is equals to order of n. Okay. So, so what we have very nice. We knew that okay, you have under the same picture, that's why they have the same kind of niche, same kind of uh, pattern on the graph. They have a linear line on the graph, and they have the same order. That is, and let's say I drew another graph. Let's say I drew another graph. Let's say one graph is this. I'm not making exact graphs. Okay? And another graph is like just below it. So the so let me change the color a bit. Is there any good colors here? Oh, okay. So the above one, let's say it is uh, some, let's say k1 log n, and this is k2 log n. If you know that, okay, the graph of the log graph goes like the positive or the right hand side of the time axis here, and it's going to come up from down and go up. Okay, they're going to like intersect here. Okay, don't go in the drawing. Okay, don't go in the right. Okay, let me correct this thing here. Okay, and obviously K1 is going to greater than always be going to bigger than. Okay. Let's say this is one here. Let's say okay, because both of them going to like give the value zero at that point. So let's say that drew one graph here like this, and the next graph like this. And let's say this is K1 log n, and this is K2 log n. Let's say, okay. So if you see in that example, rhythmic graphs, okay, logarithmic graphs. So given क्या है हमें K1 log n and K2 log n. So what is the order of K1 log n and order of K2 log n? So if you look closely, log n graph is going to correspond to the same nature. Ultimately, for the proper calculations, you are going to consider K1 and K2. But in common man's sense, the K1 does not matter to it. He's going to write log n, and for the order of K2 also is that. So the order of both of them is same. So so okay, we have investigated a lot here. So if you see what we have done here, and can you recognize this symbol here? Yeah, those of you who have studied, they can recognize that this is BigONotation. And BigONotation ultimately corresponds to the order of an algorithm or the number. I know, it's just the order. Okay, it's just the order. Okay, so what we got here till now, we understood, we learned that notation. This is order. This is equivalent to order. Okay, Vigo notation is equivalent to order. Orders of the time consumed by an algorithm. Okay, because we are calculating this at very large values of n, it does not matter what are the constants. So that's why that's the first one. When calculating the order or the time complexity of an algorithm in Vigo notation, you are going to remove constants. Constants. Second, remove smaller values. Smaller values. Okay. Let's say an example here. Let's say uh, you took, okay, you took, let's say, what is the order of 3n plus 2? What is the order? So you are going to see, okay, this is the constant, but at larger value of n, let's say n is equal to 10 to the power 6, then it's going to be 3 into 10 to the power 6 plus 2. And this number is very large, that is 3000, yes, 002. So do you think this two even matters? No, it doesn't matter. For a common man, it doesn't matter. For a scientist, it might matter. Okay. We are going to remove that. That's the power n. Now, what do you think? Like in the above example, what do you think that this thing matters? Or let's say 10 to power Well, yes, it doesn't matter. So that's why we are going to ignore it. And it's going to be n. So n is the order of this for this question. Order of n. Okay. So also the third one is BigO notation gives information at worst case. Okay. So bigger notation gives information about the worst case. Okay. So what about the best case? Okay. So that's the next Kanda. Okay. So you understood what this why I did all of this. This all was done to make you understand why bigger notation came into existence. Okay. So let's go into the next one. That is the average and the best case. One is bigger notation, then we have the theta notation, and then we have the omega notation. We are going to see the omega notation. Omega notation. Correct me if I'm wrong in the comment section, but I, I think so. The symbol is omega, and that's the ohm. So what is it? It's the best case. Best case. Okay, I didn't write it here. Okay, yes. Okay, so it gives about the best case. It's going to gives information about the best n algorithm can perform. It gives information how well an algorithm or how best the algorithm can perform. Like let's say generally we can use the bigger notation because we consider about the higher values of n. So the omega notation and the theta notation doesn't matter. But let's say as you have an array, this is an array, and you are searching an element. Search. And the search is binary. Or okay, you are searching an element. Okay. And the moment you start, you found it. So you found it. You found it. So in that case, the omega will be 1. Or you can say in that case, every time you are doing it, the order is 1 because you are like depending it. So that's the best case. And 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 there's not much in like in the best case scenario. And then you have the average case. Average, yeah, that is theta. Notation. So gives average is of and algorithm. Okay, so and it is denoted by theta. Okay, notation. Okay, so and it doesn't matter. Okay, it doesn't matter what is left. For the average case, it's not like you are going to take the best case and the worst case and take the average. Sometimes it might apply, but a lot of time it does not. Let's say, let's say for the search, the best case is when you found the element at first. Worst case. Worst case. What is the worst case? It's open, and you will be surprised, but kind of if you calculate the average case, that is over n. In other sense, you can do it like this, that you took like one plus like the bad case, and then you took the average, and then you did like your kind of high school maths, and then you did that. Okay, and then you again did okay, applying the rules here, then you are going to reduce it. You are going to say that uh, this is kind of this, and you can do like this, but no, it does not make sense like this. Okay, the average case, why the average case is like this? Because the number can be in average can be available from the very first point you start searching to the last point you are going to search to. Okay, it can be anywhere in the array. So that's why the average case here is n. Okay. Okay. So this was the thing. Most important is the big notation. The omega notation doesn't come as much and is not used at all, because when you are going to make some program, you are not going to make in the sense that it is going to always have the best case. And the average notation, it also doesn't matter, because if you can bring down the BIGO, or you can bring down the worst case time complexity down, then ultimately your best case will come down. Your average case of the theory notations value will come down. So the best idea is to bring down your BO notation, BO value, or the worst case time complexity. So that's all for this video. In this video, we have covered a lot of concepts. Okay, some physics also. So we have learned a lot about the notations, asymptotic notations, and hope you like this video. If you like, please subscribe and share with friends. And yeah, you can leave down some comments that did you like this video or not, and what you want me to improve in. Is it my teaching uh, methodology, or is it about the examples? It is about maybe anything, whatever you want. You can comment me down in the comment section, in the comment box. It's open for all. Okay. So thank you everyone, and bye bye.